Okay, I had promised that I'd make a couple video lessons to help you with the chapter 10 and 11 material for those who wanted to have a little bit of support. So chapter 10 deals mainly with, well, actually both. Chapter 10 and 11 deal mainly with properties of waves, different types of waves. And so the first part is a little bit of an introduction to the waves themselves. And then this chapter then focuses more on the ones we call wind waves, which are the typical ones that we tend to see. Chapter 11 deals more with some of the waves with longer wavelengths, the bigger ones like tides and seiches and tsunamis and stuff. Okay, so we'll start with chapter 10, and it starts off with a basic introduction of what waves are. So waves are they're disturbances which are caused by movement of energy from a source through some medium. And there's different kinds of waves. So there's light waves, there's mechanical waves, there's different types of waves. And you've learned probably about a lot of waves if you took physics. Here we're talking about ocean waves. And ocean waves are a type of mechanical wave in which energy is moving through water. Water is the medium. The energy is what's moving through the wave, but the particles of the water themselves, they really take these little circular motions, so they don't really move all that far themselves. Okay, the ones closer to the surface are going to have more movement. So the particles of water that are closer to the surface will have bigger, what we call circular or orbital movements. But the ones as you get farther down have smaller circles, and if the water gets shallower, then they'll actually flatten out and they're not really circular in motion. So orbital waves then are just what you see. Okay, so the particles of the water move in closed circles as the wave of energy passes through them. They occur at the boundary between two media. So they occur here where the air meets the water, and they can also occur at where different layers of water of different properties can exist. So if they have different densities, then they can have these types of waves that occur between them. Now, I'll show you a couple of little animations. This one is showing the orbital movements of particles as the energy passes through them. So the water particles don't really move, although to our eyes it looks like the water's always moving and coming in. It's the energy that's passing through the water particles that's actually moving. Okay, the next one is just showing what happens when there's something sitting on the water, what we see. Okay, so if there's, say, a bird sitting on the water, it looks like they're bobbing up and down, but really they're moving in these orbital patterns. They move down and back, up and forward. So it looks like they're bobbing, but they're really moving in circles along with the water particles. Okay. So, some other terms that you'll probably read about are here. They're kind of scattered through the chapter, so I wanted you to understand what they mean. One is progressive wave, and the other is standing wave. So progressive waves are ones that move forward. They can be large or they can be small, but they move forward. Standing waves are ones that are formed often by interference of other waves, and because of the way they interfere, it ends up making them look like they're stationary. They're not moving at all. So that would be a standing wave or stationary wave. Okay, so if you see them moving, then those would be progressive waves. Then another objective we have is to understand the parts of a wave. So if you've taken physics, you probably know this already, or even math. You learn about sine waves and cosine waves, sine curves and cosine curves, and this is the kind of information you learn about them too. So A wave crest is the highest part of the wave. So here's one crest, and here's another crest. Okay, highest part of the wave above average water level. So highest part above, well, you could think of the still water. The wave trough is the bottom. Okay, so the lowest part, the valley between wave crests. The wave height is the distance between the top of the crest and the bottom of the trough. So this would be the wave height. So from here to about here, from the top of the crest to the bottom of the trough. Wavelength is the distance between the tops of two crests or between the bottoms of two troughs. Okay, it's the horizontal distance basically between two successive crests or troughs. A wave period is the amount of time, so it's going to be usually in seconds. Okay, it's the amount of time that it takes, if I was watching this point right here, that it takes for this point to pass me and this point. So the amount of time basically for two successive crests to pass where you're at. So the amount of time for it to move a full wavelength, you could think of it that way too. The wave frequency, on the other hand, is how many go by. If I was standing here again, it would be how many waves can pass by me in a second. Okay? So period is how much time it takes for two crests to pass me. Okay, if I'm starting here and I started the first crest, for the next one to get past me, so basically the amount of time it takes for it to travel a wavelength. The wave frequency is how many can pass me in a second. So that's just to help if you haven't covered that material before. Waves are classified by three main things, or three main items, or properties, sorry. The disturbing force, the restoring force, and the wavelength. So first, the disturbing force, that's basically the energy that causes the wave to form. So the wind waves that we tend to see out of the beach most often is basically formed because of wind that's blowing across the ocean floor. Okay, the ocean surface, the energy from the wind transfers to the ocean surface, and then the energy is passed along, and the water particles will move as the energy moves through the water. Okay, a seiche, which we're going to learn a little bit more about in chapter 11, the disturbing force for it, or the energy that causes it to form, is the arrival of a storm surge or a seismic wave, which is like what causes earthquakes, movement within the earth itself, in an enclosed harbor or bay, or sudden change in pressure. Okay, so that's what brings about a seiche. The disturbing force for seismic waves, so an earthquake and accompanying tsunami, is landslides, volcanic eruptions, faulting of the seafloor, so how they move, how the plates move together. Okay, all those things that are associated with earthquakes. So a tsunami is basically, if you remember, it's caused when one plate is held down a little bit extra, then eventually it's going to give and let go, and when it releases back, it causes a great big wave that come in. So the seismic waves or tsunamis are caused by basically all those things associated with an earthquake. Tides, on the other hand, you've probably known since when you first learned about tides in early years, but the tides come about basically because of gravity. Okay, so gravitational forces between the Earth, the Moon, and the Sun, combined with how the Earth rotates. Okay, so gravity and Earth's rotation. The combination, that's what causes the tides. So the interaction of Earth, Moon, Sun, their gravity, and Earth's rotation. The second way they're classified is by their restoring force. Okay, so the restoring force is the dominant force that's trying to get the wave surface back to being flat. Okay, so after it's formed, it's whatever is trying to help it get back to flatness, but in the way it does it, it ends up overcompensating and causing the wave to kind of get bigger in a sense, or to keep propagating. Okay, so for really tiny waves, called capillary waves, which are the ones that are, they have wavelengths of less than 1.73 centimeters, so they're pretty small. They're like little ripples in the water, and they are started by wind, okay, but they're really small. And so the force that's trying to help them get back to being flat is the forces that are holding water together. So the hydrogen bonds and the cohesive forces that result in the surface tension, or water trying to hold itself together. Okay, all other waves, so anything bigger than the 1.73 centimeters, all the rest of them, gravity is working to try and get them to be flat again. But as it does so, it kind of makes a trough go a little bit deeper and a crest go a little bit higher, and can sometimes keep it going as a wave. Keeps it propagating. So those are gravity waves. So capillary waves, ones that are trying to be flattened, they're little ripples in the water trying to be flattened by cohesive forces of water. Gravity waves, gravity is trying to help restore them to being flat, but ends up helping to propagate them usually. The third way that they are categorized is according to their wavelength. And we saw above that wavelength is the distance between two crests, or the distance between two troughs. Okay, so if you can think of it as if the crests are more spread out, farther apart, and they have a bigger wavelength. Okay, so this is a table that's in your book as well, and it shows the four main wave types. Their disturbing force, which is the first way they're categorized, or and also their wavelength, which is the third force that we talked about. The third way of classifying them. Okay, so you can see them both here at the same time. So wind waves, the ones we typically see, tend to be from 60 to 150 meters wavelength. Okay, and what causes them is wind over the ocean. If they're really tiny capillary waves, then they're going to be flattened, or they try to be flattened by surface tension, but usually the capillary waves are pretty tiny. Seiches are pretty large wavelength waves, usually related to how big the basin is that they're forming within. And once you see a little bit more about seiches, then this will make more sense. Okay, but again, they're caused by change in atmospheric pressure, or storm surge, or tsunami reaching a harbor or a bay, or a basin area, basically, where the water can kind of go back and forth between walls of surface, or walls of land, or where it can kind of go between the edges of the bay, or back and forth. Okay, so tsunamis, or seismic sea waves, they have a wavelength huge, 200 kilometers typically. And again, they're caused by those things that are associated with earthquakes. So faulting of the seafloor, volcanoes, landslides, and tides, typical wavelength, half the circumference of the Earth. Okay, so they have the longest wavelength of all of them. Their disturbing force, gravity, so the interactions between gravity of the Sun, Moon, and Earth, and the rotation of the Earth. So this diagram actually shares all three so there's disturbing force and restoring force, and well, we know these ones have tides have the longest wavelength, then usually tsunamis, and then seiches, and then wind waves. So you could think of this as decreasing wavelength, because capillary waves are the really tiny little ripples. This is their restoring force, so what's acting on them to get them back to being flat. And then this is what kind of causes them to happen. So wind basically causes wind waves and seiches and capillary waves to start. Capillary waves are so tiny that the surface tension of the water is the main restoring force for them, whereas gravity would be the restoring force for all these other types of waves. Okay, seismic disruption, so basically all those things to do with earthquakes is what causes a tsunami. Gravity and Earth's rotation is what brings about the tides. So that's kind of how they're classified. I'm just trying to help you understand the diagrams a little bit better, so hopefully you can see this okay. The next objective is to understand differences between properties of deep water waves and shallow water waves, and which of these types of waves would be deep or shallow. Okay, so tide waves, or tides, tsunamis, seiches, wind waves, capillary waves, which ones would be considered deep water waves or shallow water waves, or could they be both, and when? So how do you define deep water waves and shallow water waves, and what are some of their features? So most characteristics of ocean waves depend on the relationship between the wavelength and their water depth. The depth is what determines the shape of the orbits of the water molecules, whether they're circular or whether they end up flattening out. Okay, the wavelength is what decides the size of the orbits. Okay, so deep water waves are waves that are moving through water that's deeper than half of their wavelength. Okay, so here, if this is their wavelength, then half of their wavelength would be to here. Okay, so it has to be deeper than this distance. Okay, so if I went this distance, then there's still water below that. So this would be considered a deep water wave. If you look at this one, the wavelength goes from here, this is the crest to crest. So if I went halfway, that would be like this distance here. Wish I could get the pen to work and stay on, but it just doesn't seem to want to. I wonder if I can. Yeah. Okay. So if I went from halfway between the two crests and I said, okay, well, what's that distance down? Okay, that's less than half the wavelength. So this would be considered a shallow water wave. Okay, the depth is actually less than 1/20th of the wavelength. When it gets to that depth, then the orbitals of the water molecules starts to flatten out. Okay, so if we looked at the wavelengths, so here's the wavelengths. Okay, so if you had a wave that was, say, 200 feet wavelength, then it would have to be 100 feet deep. Or if you had 60 meters wavelength, then it would have to be 30 meters deep in order for it had to be deeper than that, a little deeper than that, in order for it to be considered a deep water wave. And that's possible. Okay? The very deepest the deep trench, so the deepest that water can be is 11 kilometers. Okay, so in the Challenger Deep, the deepest trench in the Mariana Trench, the water is, well, it's 11 kilometers, so that's 11,000 meters. So wind waves could obviously be deep water waves because the water, it's possible for water to be so half the wavelength, so it's possible for it to be more than 30 meters to 75 meters deep. Okay, so wind waves can possibly be called or referred to as deep water waves. Seiches are large. They don't usually, the wavelength is so large that they wouldn't normally be able to be deeper than half of their wavelength. And if you look at a tsunami, they typically 200 kilometers. Okay, so half that would be 100 kilometers. And the deepest that the water could be is 11 kilometers. So it's not possible for this to be considered a deep water wave. Tides, half the circumference of the earth, again, that's super, super huge. So there's no way that it could be a deep water wave because a deep water wave, in order for it to be considered a deep water wave, it has to be deeper than half of its wavelength. And they just have such large wavelengths that they don't have the properties of deep water waves. Okay? So they always tend to feel a pull from the bottom of the ocean. So deep water waves, they can become shallow water waves as they approach a shore or things that are under the water like reefs or things like that, because at that point the water could be less than half the wavelength deep. Okay, so transitional waves are waves that are basically, they have a depth between 1/20th and half of the wavelength. So they're basically, they fall somewhere between having circular orbits all the way down and being flattened out because of the pull of the ocean floor. So the idea, or the basic things you should understand when we're talking in terms of deep water waves and shallow water waves is deep water waves, the water particles move in circles because they don't feel that pull of the bottom of the ocean floor. Okay, so wind waves that are out farther or don't are deep enough that they don't feel that pull from the ocean floor, the wave particles or water particles are going to keep moving in circular orbits. Whereas once they get closer to shore, or if we're talking waves that have really long wavelengths like tsunamis and seiches and tides, then they will always feel the pull of the ocean floor because they're not deep enough. Okay, so they're shallow and their water particles are going to be moving more in a flattened orbit, not circular orbits. Okay, so the only ones that can be deep water waves are wind waves. And wind waves can become shallow water waves. So this is a little diagram that shows that. Okay, out here, here's the wavelength of this particular wind water wave. And you can see there is half of the wavelength. That's as deep as half the wavelength. So it's obviously a lot deeper than that out here. So this would be deep water wave, deep water wave, deep water wave, deep water wave. But as soon as it comes closer to shore, okay, it starts to feel the pull of the ocean floor, and then these circular orbits start to become more and more flattened out. And eventually, the crest is going to break. And we'll talk a little bit about why that is. Okay, so here, there's a transition between where it's half, where it's right here, from where it's at half the wavelength to where it's at a 20th of the wavelength. So this would be where it'd be considered transitional, if you might. But it's not long-lived, because then it would become shallow water wave. And the wave would break when it reaches a certain ratio of wavelength to wave height. Alright, so if you were wanting to figure out the speed, okay, so the velocity, or how fast the wave energy is moving through the water molecules, water particles, okay, you can use certain formulas. Wavelength is pretty difficult to determine at sea, but if someone were observing, they could time and figure out the period, or how long it takes for two crests to pass. Okay, so if you're starting with the first crest for the other one to pass, then that gives you the time it takes for it to move one full wavelength. Okay, so while this is the formula for velocity, so you have velocity is wavelength over time, we can use their period and a relationship between the period and velocity in order to calculate it right out using the period. Okay, so if you wanted it in meters per second, you'd say velocity is 1.5 times the period. If you wanted it in feet per second, then it would be 5 times the period. Okay, so that's for deep water waves. Now it becomes a little trickier when we're talking shallow water waves, because as the deep water waves move into shallow water, their velocity is going to change because of that pull of the ocean floor. Okay, so their velocity and their wavelength starts to change, so you have to use a different calculation. So this is the formula you'd use instead. And g is acceleration due to gravity, so it's a known value. This is just simplified. If you took the square root of g, then it's approximately 3.1. So you could say velocity is 3.1 times the square root of d. And d is the depth of the water in meters. So it's relating the velocity to their depth, because as they become, as as the water becomes shallower, then it's going to affect the velocity. So if you were kind of looking at deep water wave versus a shallow water wave, so for instance, a seismic wave, remember that's a tsunami. So the period for a deep water wind wave is about 20 seconds, up to about 20 seconds. And their wavelength can be up to about 600 meters. So their speed, if you calculate it, would be up to possibly 112 kilometers an hour. As opposed to a tsunami, where the period is about 20 minutes. So it takes about 20 minutes for one wavelength to basically pass by a given spot. The wavelength is up to about 200 kilometers, so much bigger. The speed, if you calculate it, is typically up to 760 kilometers per hour. So that is unreal, the speed that it comes in at. So that's why when a tsunami hits, it's just it can be very, very devastating. Okay, so if you look at the wavelength and compare it to the speed, the longer the wavelength, the greater the speed, or greater the velocity. Okay, so this would be a good relationship to kind of remember. Alright, I'm going to stop there for this part of the video, and then the next part of the chapter focuses more on the wind waves. So the wind waves, again, they're the ones that we typically tend to see. And if you look at their properties, and they have the smaller wavelengths. Okay, they're caused by the interaction with the waves, or with the wind over the ocean. So we're going to look at basically the typical waves that we see and some of the properties that they have. And then chapter 11 deals with the other types of waves, the tides, the seiches, and the tsunamis. Okay, so I'll end this part here.